Hello, Physics 1. Welcome to your last physics lecture. Woohoo! All right, so we're going to continue on with chapter 11. By the way, we are going to be stopping after we go through the section on how you can predict rotational motion using the angular momentum principle. We obviously always skip over the computational sections as we don't do VPython in this class, and I'm not going to go into angular momentum conservation as it has to do with the atom. All right, so equilibrium basically has to do with if you've perfectly balanced something. There's actually a Curious George episode about it. Very, very cute. George is trying to balance things on different bars of woods and find the fulcrum point and so on and so forth. So if you need some fun watching this weekend and you need it to apply to your physics class, Curious George has you covered. He doesn't do the equations though, he just finds it by feel. All right, so if torque is equal to 0, then the change of angular momentum with respect to time is equal to 0. Then it follows that if the change of angular momentum with respect to time is equal to 0, this implies that the net torque is equal to 0. So sometimes you have one and you imply the other, and sometimes you have the other and you imply what you're missing. So we're going to look at an example of equilibrium. This is a Curious George example. Well, Curious George does this in the episode. All right, so let's say you've got two people on a seesaw perfectly balanced. So person 1 is over here, so you have M1G going down. You've got the normal force going up at the axle, and M2G going down. As you'll see, these people do not have the same mass. So person 1 is sitting distance 1 from the fulcrum point. Person 2 is sitting distance 2. So M1 is equal to 85 kilograms. D1 is equal to 0.5 meters. M2 is equal to 35 kilograms. So there's two things we want to know. We want to know what is the force, the normal force at the axle, and where is person 2 sitting. So we know this has perfectly balanced, but where are they sitting to do this? So basically, this is something you're probably familiar with, whether or not you realize it or not. So if you've ever balanced, this pen is not equally weighted on both sides. But I can find the point at which I can balance it on my finger. And if I move it slightly off that point, it falls. So that's what has happened. Okay, so we're balancing our system, and our system is two people plus the seesaw. The surroundings is Earth and the axle. These are doing force on the system. They can do work on the system. Okay, so we'll start off with the momentum principle. So we know that the change in momentum of the system with respect to time is equal to the net force. The system is not moving. Therefore, the net force is equal to 0. So our normal force minus M1G minus M2G is equal to 0. So the normal force is equal to M1 plus M2 times G is equal to 85 kilograms plus 35 kilograms times 9.8 newtons per kilogram. The normal force is equal to 1,176 newtons. Not surprising. You probably all saw that coming from a mile away. What you learned in chapter 1 is still good in chapter 11. See? look at how much you guys have accomplished this semester. You should feel very proud of yourselves. I'm proud of you. All right, so moving on to the angular momentum principle. So we've learned what we can with the momentum principle. Now we need a little bit of angular momentum. So the change of angular momentum with respect to time is equal to the net torque, which is equal to 0. It's still not moving. Let's make A easy. A is the axle. And we've talked extensively why that's generally a good choice. Let's make our lives easy, people. So L will be in Z because everything else is in X and Y. So we can consider just that coordinate. And you can either get that coordinate by doing the IJK method of a cross product, or you can memorize the formula and use just the Z coordinate. When in doubt, always do a cross product version. It's just a really good way to double check yourself. So I actually always use the IJK method through Physics 1, Physics 2, into my first semester of modern physics and electromagnetism. Because it was just a really good way to prevent making mistakes and overlooking something simple. So there really isn't a right or wrong method to choose, but I really encourage you to practice all of them and see which one gives you the smallest margin for error. Anyways, the one that you're least likely to make mistakes with. Do that. And show your work every single time. That helps. If you are making mistakes, it helps me see where. And it helps me know it's just calculation mistakes are different than conceptual mistakes in terms of their weight. So again, do the easiest form of a cross product for you. And this may vary based on your experience of whether or not you've done cross products before. Okay, so the Z coordinate, which you've either gotten using the IJK method or you've just memorized the formation of the formula, is M2 or M1G D1 minus M2G D2 equal to 0. Therefore, D2 is equal to M1 over M2 D1, which is equal to 85 kilograms over 35 kilograms times 0.5 meters, which is equal to 1.21 meters. Rather large seesaw. By the way, this is another example of statics. So for those of you who have an MCAT in your future, the MCAT seems to really like static problems. So this would be another area where you'd want to make sure you spend some time doing practice problems even beyond just what's in this book. So one of the things that as you're prepping for standardized exams, you want to learn what do they tend to favor, and then you do more practice in those areas. And it just depends on what exam you're taking, what they favor. I took the physics GRE. I don't remember many static problems. They tended to favor other things. Okay, so moving on. I think I've blocked a lot of the physics GRE out. Ugh. Talk about exams I never want to take again. All right, predicting positions when there is rotation. This is the last section we're doing in chapter 11. And we are not doing chapter 12. We'll do that next semester. All right, so to model a rotating system, we need to predict its position. And this means predicting the angle of rotation. So let's do an example. You have a wheel wrapped in string and you pull it to make it turn. Okay, so it has a radius r. We've got some mg force coming down. Your hand is pulling a string, which is making it turn. The axle has a normal force on it. By the way, the center of mass is not moving. It's just the wheel is spinning. And it's spinning through some delta theta. So this problem starts in motion. And it has some moment of inertia, I. Okay, so let's write a few things down. Wheel has radius r, moment of inertia I, mounted to an axle. Axle rose, wrapped in string. Pulled with force F. And then it does have starts with omega I. So it does not start at rest. Although I suppose this would work if it did start at rest, what we derive. Okay, you just put a 0 in for omega I. Okay, so we want omega final after delta t, and how far did your hand move? All right, so solution. Our system is the wheel plus string and the surroundings, earth, axle, hand. The momentum principle, dp dt, is equal to F net, which is equal to 0 because the center of mass is motionless. All right, so that's all we can learn from the momentum principle. Now let's move on to the angular momentum principle. All right, so since the center of mass is motionless, we can imply that there is no translational angular momentum, so we're just dealing with rotation. So the angular momentum rotational final is equal to the angular momentum rotational initial plus tau net delta t. So we're using the update form because we know omega I, so we want to go after omega final. And we know expressions for angular momentum in terms of quantities we were given. So this is a problem. We don't have any numbers. We just have concepts. So we're going to solve in terms of I, omega, r, etc. So I omega final for L rotational final is equal to I omega initial plus tau net delta t. That's just r, f, delta t. And so we want to solve for this, omega final. It's equal to omega initial plus r, f, delta t over I, and done for part 1. Beautiful. All right, so how far did your hand move? So for this, we need theta. Okay, so because if you think about it, it's really bad theta. As you're pulling string off, you're changing delta theta, which that arc length will correspond to the distance that your hand is moving. So we need to go after the rate of change of the angle theta and how it pertains to angular speed. So, angular speed is equal to d theta dt, which is just another way of writing delta theta, delta t. Delta theta is equal to omega average times delta t. Omega changes at a constant rate. RF over I. So omega average is equal to omega I plus omega F. The reason we know it's a constant rate, we weren't given a changing force. Divided by 2, therefore, see, all the stuff we learned comes back. Delta theta is equal to omega I plus omega 2 over 2 times delta t. All right, so we can use this now to get after length. So if theta is equal to 2 pi radians, the hand moves 2 pi radians. More generally, for delta theta, the hand moves r, that's an r, delta theta. So the change of x for your hand is equal to r omega I plus omega final over 2 delta t. And we got there. All right, so that is the end of Physics 1. So we've talked about the angular momentum principle. We've learned about how we can use this to express conservation of angular momentum, to find torque, to predict rotation, just like we have with all the other principles. So I would like to end, I had a really cute video pop up of my daughter. I was teaching her physics words when she was 2, and she ends the video on a cute note. So I'm going to see if I can't play this for you. So this is the amount of enthusiasm I hope all of you, and yes, I know, I'm just zooming into my phone. So there she is as a 2-year-old. She is now 4. She still has a messy face.
Dynamics. You say quantum electrodynamics.
Quantum electronics.
Yay!
Yay!
Can you say quantum chromodynamics?
Quantum matrix.
Let's try that again. Can you say quantum
Quantum matrix.
chromo
Chromo matrix.
dynamics?
Dynamics.
Yay!
Yay!
Can you say dark matter?
Dark matter.
Yay!
Yay!
Can you say neutrino?
Neutrino.
Yay!
Yay!
You say quark?
Quark.
Yay!
Yay!
Do you like physics?
I do like physics.
And I hope that's how at least some of you feel after taking part 1 of this class, that maybe you've developed an appreciation for this field. I know I'm realistic, it won't happen to everybody, but it's been fun. I will see you next semester for Physics 2.